Hi everyone. I don't think anyone has joined, so let's wait for some time. Hi Rohi.
Hello.
We'll just wait for a minute or two, see if others are joining in, else we'll start. Yeah?
Hi, Bhamik.
Hi Saransh.
I can view it over screen now. Working fine.
Okay.
I guess an update was missing, so I just loaded that plugin.
Okay. Then maybe we can give it a start. I believe you can see my screen, right?
Yes.
Okay. Okay. Uh, okay. So basically, what we are going to do is that we have looked into the stats model library. We have also looked into sklearn. Let's take a quick pause until this time. If there is any questions that anyone has, let's try to clarify that first. And then we can continue because we need to now move ahead from the basics and start looking into problems or start looking into cases which are more industry oriented, where there will be problems with data, there will be variations in data and so on. But before we move in there, at least until what we have covered, this should be clear, or there shouldn't be much of a doubt in here. If there is any doubt, let's try to talk about it now.
Bhamik, just one thing I just wanted to know the broader difference between adjusted R square and R squared.
Okay. Okay. So basically, what you are doing in case of R square is that you are simply trying to prepare, or you are simply trying to understand what is the measure of the fit, right? So it takes a form of a proportion, as we have seen, the proportion of the variance, right? So you are simply trying to explain the proportion of the variance by taking a formula like 1 minus RSS divided by TSS, right? Now, in other words, you can, if you look at this formula carefully, then you can also say R square is equal to TSS minus RSS in the numerator, and then in the denominator you have TSS, right? Then you can try to relate this, right? I hope I'm making sense. So let's try to write this. Okay, let's do one thing. Let's create some. Okay, well, yes, no, it is working fine, right? Yeah. So let's just create a few cells, and I would just like to write, yeah, here. So let me just take my pen. Okay, and so what we are doing here is basically what we are saying, R square, R2 I will write, is equal to 1 minus RSS divided by TSS, right? This can also be written as R square is equal to, in the numerator you can have TSS minus RSS, right? And in the denominator you can have TSS, right? So you divided this TSS by this TSS. So what you're doing is this TSS and this TSS is going to cancel out each other, making this one. and then the remaining part, this RSS divided by TSS, it remains, and you get a formula like this. Now, what you're trying to do in this case, as you can understand, you're trying to explain the variance. If the variance is very big, then this value will be very small, right? In which case you have not captured a best fit line, because a best fit line is ideally supposed to capture the right amount of variance. So let's say you have a lot of data here. Okay, you have a lot of data here, and then there is a line over here. So barring these edge cases, these 2 points which are edge cases, maybe these 3 points, everything else is covered. So you are covering a lot of points. Hence your R square value is going to go up, right? But if I have a best fit line which is something like this and it is not covering all the points, then my R square value will come down, right? So this is a very good measure, but then R square has a problem. Okay, in any case, R square has a problem. Let me just clear the drawing, and I will explain what is uh, adjusted R square, right? So if you see over here, R square has a very common issue. The common issue is, okay, 1 minute, and one person is pinging me. Can okay. Yeah. So as we increase the number of independent variables, let's say in our equation, we are doing this 1 minus RSS by TSS. Okay. If the number of independent variables are going to increase, the value of R square is also going to increase. Right? The value of R square is also going to increase. Right? We can prove this also. We can take a lot of variables and try to do this. Okay, we are going to do that, right? As part of the lab also we are going to do. So this usually comes into effect not in simple linear regression, multiple linear regression, right? So the more features we add, right, this value, okay, becomes smaller. Why? Because this value increases. The denominator is going to increase because it is taking the total sum. And because the denominator is increasing, this value becomes less and less, and then this value becomes closer to 1, right? And the R square value increases. That is that really signifying that your model is good? No. In that case, your best fit line estimation, or the value, which in this case is R square, that you are using to say whether your R square or whether your line is really a good fit or not, is really not the right thing to say. Why? Because simply you have increased the number of variables, R square has increased, and now you are saying you have a better model. It may well not be the case. You may have taken features, which we are going to see when we do multiple linear regression, is where you have features which are intermingled with each other. They have very high correlation with each other, causing a problem of multicollinearity. Multicollinearity is a very common issue where features are interlinked with each other. They are interlinked or correlated within each other rather than, or even if they are correlated with the target, in which case R square does not prove to be very useful. So this is where adjusted R square will come into picture, right? So as we increase, as I said, if I increase the number of independent variables, the R square value increases. That doesn't mean that the new independent variables have any correlation with the output variable, right? In other words, we have to do the analysis first of all to understand what is correlation and all these things. But even with the addition of new features in our model, it is not necessary that our model will yield a better result, right? But the R square value keeps on increasing. Now to rectify this problem, what we do is I take the R square value. Let's say this is my R square value, and I have to penalize this. I have to penalize the excessive use of features that I have done, right? How do I penalize this value? Is by creating this adjusted R square thing, right? And adjusted R square is nothing but I'm going to divide, right? I'm going to divide the R square, okay, by the sample size, right? So adjusted R square is nothing but this. Let me just take a pen like this. So I'm going to write R adjusted, okay, bracket A, yeah. R adjusted is going to be 1 minus something, okay. We are going to look at this something. Sorry, this will be 1 minus, not A minus. This 1 minus something will be there, and the formula is something like this. So the formula will be something like this. multiplied by this. Okay, and then there is a denominator. So let me just try to do this. You see 1 minus a component, and that component has two things in the numerator, one thing in the denominator. What is there in the numerator? 1 minus r square. Right, so I'm taking an absolute value now of r square, and then I am multiplying it by n minus 1. N is the total sample size. In our case, in our example, this advertisement data set that we have taken, we have 200 examples. N minus 1 is basically my degrees of freedom, right? Then what I'm doing, sorry, I think I've chosen a wrong place. It is not going to extend here, right? So in the denominator, what I do n minus p minus 1. Let me just extend this. So n is the sample size. N is the sample size. Okay. P is equal to the number of predictors. Predictors or my features. And r square is obviously my sample r square. Okay, the one that I have already calculated. Right? So in this way, what I'm trying to do, I'm actually penalizing it. And I'm also taking into consideration the degree of freedom. Similar kind of activity we did in the ANOVA examples, where we tried to penalize the equation by taking into account the number of variables I have. What this is going to do, it is going to nullify, or it is going to minimize. It's not going to nullify. I'm sorry, that's the wrong word. It's going to minimize the effect of more and more features being taken into account when I'm trying to do any kind of regression problem, irrespective of whether it is a linear regression, it is a polynomial regression. There are two other kinds of regression which we have to see. One is called ridge, and other is known as lasso. But in those cases also, in those advanced cases also, it is not going to matter much, right? The effect will be a little bit under control, right? We will do a small exercise on this maybe as well to understand what we are doing. When we look into multiple linear regression, we will come to know what is happening over here, right? But in our case, when we are doing simple linear regression, we won't be able to understand this problem right now, right? So I hope that was clear. If you have any other doubts. Let me just see, there's some chat over here. Yeah.
Yes, Bhumik, it was clear.
Okay. Fine. So let just a moment. Yeah. So until last day. Okay. No, I'm sorry. Is there any other question? No, right? Fine. I'll take that as a no. Let's try to continue. So what we are going to do today, we'll start with something which is like I will not say advanced, but it's kind of things that we need to consider when we are doing the modeling. So I'm going to write as I explain. Yeah, so what we are going to do is yet another issue with R square, okay, or yet another issue with the model, yet another issue with values like TSS and RSS and all these things, because of which R square has come into picture, but it does not always entirely nullify the effect of the problem which was already there in RSS and TSS. Let's try to explain what is R squared value, which is used to find out if my model or regression line is a good one or not, is calculated by means of what? By means of RSS and TSS. Right, we have already seen R square is equal to, I'll just write it down over here, 1 minus, okay, RSS divided by TSS, right? If I have the same model and the same data set, and I increase, or I, sorry, increase is the wrong word, I change the scale, okay, scale at which, just a moment, the scale at which the data, the feature and targets are represented, especially the features, then again we will land up into a problem. Okay, okay, what is this problem? The problem is not with the calculation of the best fit line metric. Okay, best fit line metric is already calculated by R square, and the way I have created the formula dividing RSS by TSS is already taking care of most of the problems caused by this thing, right? But there is one problem that has now come into picture. The moment I increase the scale, okay, let's imagine that I have a data set where I'm taking weights in kg, okay, and I'm trying to estimate the height. Okay, so what I'm doing is I have two columns. Just a minute. Okay, I'll just save this line so that it does not go away. So I have a data set where I'm taking weight and I'm trying to estimate height. Maybe a very bad example, but I think I can prove my point. So what I'm doing is, let's say a person whose weight is 10 kg, okay, 10 kg, has a height of I don't know, 2 feet, right? A person who has 11 kg weight has a height of 2.1 feet. So essentially what I'm saying, my scale of weight is kg, my scale of height is feet, right? So I create a data set like this, or I do a sampling of a data like this, then I fit it into my model. And obviously my model is going to give me that hypothetical equation y is equal to mx plus c or something, which is going to give, okay, something. And then I'm going to find out the y unknown basis any value of given x, where x given is my weight and y unknown is the height I want to find out. My model is ready, it is tested, it is verified, all the tuning, all the parameterization, everything I could mathematically do is already available. Okay, if that is already done, then my model is ready to be used into production. So let's say I take this and I somehow deploy this in some server. Okay, so this is some server, this is some hardware where my model is there already. Okay, so my model is here now. Okay, once my model is here, what I am saying is, let's say there is any user, let's say Saransh. Okay, he has to input the value, right? He has to input the value to train the model from time to time, because this one-time training is not going to help. He has to train the model. So I trained this model first of all with the data D1. So I put this data D1 into this server. The model got trained and now it is ready. I can simply give an input. Weight is equal to 12 kg. Okay, please tell me what is going to be the height. Okay, just a moment. Okay, so weight is equal to 12 kg. Give me the answer. The model gives me an answer. Fine, it is approximately equal to 2.2 feet. Okay, so the answer I've got. So all the calculations of R square and everything and gradient descent, OLS, is everything happening within the model. Okay, so it is using some kind of computational power, CPU memory is being used. Now in the second equation, or in the second iteration, I'm sorry, let's say there is some data set D2 which Saransh has. He wants to train the model with the D2. Over a period of time, D2 is, let's say, a better version of D1. So let's say in D1, I had only 50 people's weight and height. Now Saransh has done a sampling of 500 people. He has D2, he has 500 people data, and he is going to put this into my model, into this server, into the production. The model will be trained, and then I'm going to give it an input, and then it is going to give me an output. The only problem here that Saransh has not taken care of, maybe because I did not create the documentations in the right way, he has not taken the weight in kgs, he has taken it in gram. Even worse, tomorrow he inputs another data set D3, God knows why, and he has taken weight in milligrams. If he converts this kg into grams or into milligrams, the scale is going to change. Now, is that really going to affect my R square score? The answer is no, because R square is already taking care of the scale changes by means of considering RSS and TSS, right? So not a problem with R square. The problem, okay, the problem is, if you remember this diagram, right? The problem is going to be in this. What is x-axis? The value of thetas. What is y-axis? The value of j of theta. Okay, what is this? We are trying to do a cost minimization, right? We are trying to minimize the cost of reaching that local minima. We are trying to reach that local minima where I have least error. How much time is that going to take to reach this minima is going to be determined by what scale I am using, because bigger the number, bigger the calculation. Or even worse, if I am a very smart programmer and I've created a model which goes into production, I'm going to by hand, okay, by default verify what kind of scale is being used, right? If I see there is 3 places, then obviously it might be in grams, right? Because I will not expect a person working, let's say this setup is for people working in companies. So people working in companies will not be 110 kg weight. If there is really a person, I should be worried. But if it is more than 3, let's say 4 digits, then I have to convert that into kg and all these things. So all these kind of smart calculations are already done inside my code. If that is the case, then my code is even more computational heavy. So what I mean to say is, based on the kind of scale that you're going to choose, or the calculations which are done to handle such edge cases within my model, within my program, this local minima receivance, or the time it takes to reach this local minima, increases. Okay, this time is otherwise known as the time it takes for a model to converge. It does not converge at the right time, okay, or within the right time. So it is taking a lot of time to create the model, to compile the model, or to build the model. The model is taking a lot of time to get trained. Okay, now we are playing with data sets which are very, very small, 200 lines, nothing. I just saw a use case that day where we are not doing a regression problem, we are doing something else. But there is a CSV file, which is my training data. That CSV file is 2.1 GB in size, right? Imagine a CSV file which is 2.1 GB, approximately billions of rows will be there. Just try to understand how much time it is going to take for that model to converge if I have that bigger data, and then I have done this blunder, this mess with scales, right? This is the reason why, this is one of the most important reasons why we need to do an activity with my data, right? We need to do an activity with my data, otherwise known as scaling. I've briefly mentioned scaling in the last video, but I'll just quickly do this here. The problem is not with the calculation of the base fit line metric or R square. The issue is with the input or training data being in different scale than what the model originally expected. Okay, in this case, basis the good programming done in the model, done in our model, it would not fail, but will merely take a lot of time to converge during the gradient descent, or during the uh, let's say during while when it is trying to minimize the cost function of the regression line, right? To avoid this, in production use cases with very huge amount of training data, irrespective of the format of the data, we need to perform an activity called scaling, right? Scaling can be, oh, I'm sorry, let me just scroll here. Yeah, scaling can be overall 2 types. There are more, these are only common types. Okay, there are many forms of scaling. You can do scaling in a lot of different ways. You can actually invent your own way of scaling depending on your business problem. Okay, depending on your context, you can actually create your own method of scaling. But the most commonly used in the industry are 2 things. Again, that seems to be some problem. Okay, yeah. So the most popular thing is that we are going to have a scaling technique which uses minimum and maximum value and tries to scale my feature. That is called min max scaling. And the second one is known as standard, okay, scaling. Okay, okay. It looks something like this. Okay, min max scaling. Okay, it is very easy to find from the internet. Let's not try to uh, learn something more. Okay, so we can clearly find this here, or even better, there was another link which I can open, min max scaling. If I search, there's a very good Wikipedia page on this. It's going to really be helpful. I'll just ping this link over here. Yeah, there is one thing I wanted to note here as well. There is, because of some reason in our LMS, right, I'm not able to add external URLs other than video URLs. I don't know why that is the problem. So what I'm going to do these days, or what I'm going to do from today onwards, I'm going to write things like this. I'm just going to further reading, I'm going to just say the link over here. Okay, so that you can directly link it from here. So feature scaling is a method used to normalize the range of independent variables, right? It is also known as data normalization, right? As simple as that. Now, rescaling or min-max normalization is what we are talking about over here. What it is doing, it is taking a new value of x. So that value is x bar. Okay, this is the new value of x bar. Okay, what is x? X is one of my independent variables. It's taking the min of x, subtracting the mean from each value of x. Then it is taking in the denominator the max value of x and min value of x. So this becomes the range. The denominator is the range. Clearly, it is the range. What is the max value of x? What is the mean value of x? Let's say in my case, my x is what TV. Whatever I have spent in the advertisements when it comes to TV. And my y is what? My sales, right? So y is my sales. So I'm not going to consider y over here. Y will not be considered. Scaling I'm doing for the independent variables. Okay, always note, scaling is not required for the dependent variables, because dependent variable is what I'm going to approximate. Dependent variable plays hardly any role when it comes to cost minimization, right? In the cost function, main thing is what? Theta 0, theta 1, right? In simple linear regression, j of theta, or the cost function, is defined by the parameters theta 0 and theta 1. We are trying to find the best combination of theta 0 and theta 1 so that we can reduce the value of j, right? In this case, are we considering anything related to y? No. Hence, I don't need to tune anything related to y. I'll only consider this TV variable, which is my x. So x in our case becomes TV, right? Whatever value I have. So I have some, okay, I have each and every value. Let's say this is x1, this is x2, and ultimately I have what? x200, right? I have 200 rows. So x200 is there. Now, out of this, there will be a x min, and there will be an x max. Okay, big X I have drawn. So this is the max value of the values present in the TV column, and then the mean value. I take the range, put it into the denominator. In the numerator, I take each and every value. And subtract the minimum from that value. So I'm just trying to say how much each individual feature value is distant from the minimum value, right? Then I get another new column, which is my X bar. So I say this is my new column, which is TV bar or TV scaled, right? And I'm going to write all the values over here. Let's say X1 bar, then X2 bar, and ultimately I take all the values and I do X200 bar. Clearly you can understand this is a very, very heavy process. Even if I'm doing individually for one column, in multiple linear regression I can have, let's say, 50 columns. So I have to be very performance optimized. My program must be really optimized in terms of execution. So which library am I going to use? This is basically a 1D array, and the best library to be used on top of 1D array is NumPy. The underlying scikit-learn, the library that we were seeing, like scikit-learn, underlying scikit-learn, it makes use of NumPy. It makes use of NumPy to do this kind of processing. Hence, we can directly use sklearn, and that is exactly what is being done over here. Let me just clear the drawings. It is using, okay, it is using this function min-max scaler to transform the features by scaling each feature to a given range. This estimator scales and translates each feature individually such that it is in the given range on the training set between 0 and 1. This is the main thing about min-max scaling. The output of min-max scaling, you take any data, and this is going to be proven. You can take any data and you can do min-max scaling, and you'll come to know that you take any set of data, let's say RTV ad cost, its mean value will now become 0 and max value will become 1. Okay, this does not belong to TV, this belongs to TV bar, the new variable, right, that we have scaled. So the scaled output is always in the range of 0 to 1. Okay, so this is what we are trying to find out, right? This is exactly what we are trying to find out, right? There can be different transformations. There can be different transformations used by each and every library, right? And then we can try to figure out how to use this as well. Let me clear the drawings. If I come down, I can clearly see how it is going to be used. There is an example over here. You see, this user is taking some data, creating an object of min-max scalar, and it is printing just the scalar dot fit. Okay, so it is doing a scalar dot fit on the data. Okay, which is this, which is a 2D array. Then what it is doing, it is printing the max value. So it is kind of 1.1 in this one. Okay, and then it is simply transforming the data. Once you have transformed the data, only fitting the data will not help over here. You have to use two functions. Fit, you have to absorb the data. Transform, you have to actually replicate the action, right? The moment you transform, it becomes this. You see all of the values over here are within the range of 0 to 1. Okay, that's exactly what is happening over here, right? And then we can make use of this data while training. Now, because this data is now scaled, I don't want to know what scale in which that set of data, that set of input D2 or D3 or D4, I don't want to know. Whether your weight data was given in grams, kilograms, milligrams, nanograms, I don't care, right? Because if I'm going to use a scaling technique like min-max scalar, and that is the another one, because min-max scalar sometimes is not really industry suitable. We will describe this in the next class because we may not have time now. So in the next session, we may want to look into, or maybe you would like to try to investigate from your side as well, like a homework kind of thing. Why min-max scalar is not always used when it comes to industry applications. Okay, there is a big flaw. Okay, because of that flaw, it is not always used, right? But feature scaling is really important. And by the simple method that we have done over here, what we have done clearly is that we have reduced a lot of code that we had to write. It is already written for us in optimized languages like C++. You're simply making use of the variable, making use of the functions, scaling the data, giving it within the range. I don't want to know in which scale you have entered it. I've scaled it now. My J of theta finding, this activity of minimization of the cost function is going to be very fast. I'm going to reach the minima very quickly, and hence I'm going to very quickly reach to the values of theta 0 and theta 1. The more faster it is, okay, the more reliable it is. Why is this the case? Because there is a very big probability my model is taking 5 hours to compile, and within that time there's something wrong that happened with my server. My server is down, my model is gone. Right, what I mean by my model is gone, obviously it is a software, right? I can redeploy it, that's not an issue. The issue is my training time is gone, I've lost 5 hours. It's a very, very important loss, because for critical business functions, especially in the financial domain, loss of 5 hours is a big, big thing. It's like we are working 9 hours a day and we have lost more than 50% of our day because we started compiling a model where you have entered the value of weight in nanograms, and it took 5 hours to compile, while if you would have used scaling techniques like this, it would have compiled within half an hour. So what you are doing over here, basically, let's try to clarify this. We are not doing anything which the algorithm could not do by itself. This is a very common misconception, that if I do not do scaling, my algorithm will not work. The answer is no. Algorithm will still work. It will still converge to minima, just a matter of time. Now, you have to decide, right? You have to decide, do you want to give me food to eat which is already prepared, or do you want me to give processed food which I have to put it in the oven, I have to apply some butter, I have to apply some oil, and I have to microwave it for 10 minutes. Then I have to grill it for 20 minutes. So if you are going to give me food as well as a quick, well, it's a recipe, it may not be a very big challenge until and unless while I'm preparing the food, the electricity is gone and I don't have inverter at my house. So these kind of operational problems will cause issues. right? So if you are going to prepare the food for me, then the advantage is now all those operational issues, or many of those operational issues, are taken care of. I don't need to worry about the setup, the input data, the scenario, how powerful the server is, how not powerful the server is, and all this, right? When we go to cloud, when we are going to look into things like deploying a machine learning model, we have to use cloud. We are going to mainly use, let's say, Google Cloud or AWS. But then the more you spend on consumption of CPU and memory on cloud, right, the more it is going to cost. So there is a cost aspect as well, right? The better scaling you have done on your data, the quicker the cost function is going to converge. The quicker the cost function is, lesser the CPU, lesser the memory, lesser the cost, and lesser the risk of the server going down, right? Hence, there is a reliability. So production scale system requires the reliability, right? That is the thing that we are trying to look over here. Now, the other kind of, say, there are other techniques as well, okay? You can use the Z-score to normalize and all these things. The other normalization is this, okay? Z-score, using a Z-score, can I use the normalization? I think I can do, okay? This is called standard scalar, okay? Sklearn standard scalar. So I will directly go to the documentation now, and I will also give you, oh, sorry. Min max scaling, I should have given the link. Min max scaling, why is it not opening? 1 minute, it should open. Yeah, now it has opened. So let me just take the URL. I just don't want to miss out on the URL, because as I said, I noticed I'm not able to do that from our LMS, so not sure why. So let me close this and standard scalar. I'm not doing one important thing. Please do that when you are trying to look into the documentation. Verify the version that you are using. Okay, so this is the standard scalar, and I'll just paste it over here, and I'll just write it there. And then from the next class, we can do the scaling, and we can try to do more math on it. But the standard scalar is as simple as, we can handle various kinds of data. This is like Z-score, right? Irrespective of the dimension of the data, this is the power of standardization. Irrespective of, or Z-score normalization, irrespective, okay, irrespective of what is the dimension of the data, I can do a general, okay, a general math, okay, a general math that I can do using simple things like mean and standard deviation, okay, and not minimum value and the range. Okay, the only difference you see over here is that earlier there was min, right, min, and then there was a range, right? In case of rescaling, in case of min max normalization, I'm simply replacing this min, min, with MEAN, right? I am actually replacing this with the arithmetic average or numerical average. Okay, just a moment. Okay, and then in the denominator we had range. Now I am actually taking the standard deviation. Why? I am simply nullifying the effect of scale, and I'm also trying to take into account I can have innumerous number or numerous dimensions of variable. I don't care anymore now, right? This is the biggest advantage of using standardization. Okay, this is the biggest advantage of using standardization, because it can handle any kind of value, right? It can handle any dimension of value, and that is exactly what is being used in this class. This is actually a class. So sklearn.preprocessing.standard scalar will create an object, and then we are going to put the data. It's going to scale it for us, right? As simple as x minus u divided by x, where u is the mean of the training samples, right? And s is the standard deviation. You can also turn this u into 0. Okay, there is an option in the library where you can say with mean equal to false, and then it is not going to use this minus u, it's simply going to do x minus s, right? You can also convert this this s into 1. Okay, how you can use this function? Use std is equal to false. Please don't use with mean equal to false or with standard deviation equal to false if you yourself have not sampled the data. This is my request to both of you. Please don't use these options if you have not yourself sampled the data. If you have yourself collected the data, no problem. Someone else has collected the data for you, please scale the data. Okay, let's make a stop here. I don't think we have more time now. We are going to continue tomorrow. Okay, thank you so much. Thank you.
Thank you.
Thank you.
Thank you.
Thank